Hi, I'm Rachel Meliotis, a senior editor at O'Reilly Media, and I am here with Alan Downey. And he is a professor at Olin College and also has written 3 books with us, Think Python, Think Complexity, and Think Stats. Thank you for joining me.
Thanks. It's great to be here.
Great. So we are going to talk a little bit about why you think it's important to think like a programmer. So tell me a little bit about how you think that things change when you're thinking in natural language, math, and code.
Well, I think that's where a lot of programming starts. I think of it, it's the first phase for a lot of programmers. It was the first phase for the field, that a lot of programming was taking these solutions that had been written in math notation and then translating them into code. And that's why Fortran is called Fortran. It was formula translation. And that was sort of the first phase of programming. But I think there are more steps that come after that. So one of them, I think, the more coding you do, you start to learn things by writing code. So a lot of my students, if we're studying statistics, so this comes up in Think Stats several times, one of the ways that you understand basic statistical analysis is that you do translate it into code, you implement it, and that's how you convince yourself that you really understand what you're doing. But there's also, you can run experiments. So we do the central limit theorem. You can run an experiment to confirm that it's really true. It's different from writing a mathematical proof. You test it out, and you get to see how it works when it works. You get to see how it breaks down when it doesn't work. And so I think that's one of the ways that by writing code, you come to understand things better.
And so one of the points that you had made to me earlier was that what's great about learning code is that by doing, you can see right away what's wrong because it equals an error. Can you extrapolate on that a little bit?
Yeah, and I think of that as being maybe the next phase of coding, where rather than taking someone else's solution that's written in math and translating it into code, you're now thinking in a natural language. You're thinking naturally and coding in the language that you're thinking in. So what's happening there is you're now taking your understanding out of your head, you're expressing it in code, and now all the time that you're debugging the code, you're also debugging your brain. Whatever's wrong is in the code, and by fixing the code, you're fixing your own understanding.
Interesting. So you're basically saying that better code makes you think better.
Right. And I think maybe that might be the third phase of all of this,
okay.
where now that you're really thinking in code, one example of this is that you start to understand what things are by thinking about what they do. This came up, I've been working on an example implementing linear algebra in Python and thinking about spatial vectors and frames and transforms, which are some of the pieces for working with objects that rotate and translate in 3-dimensional space. So there's a basic idea of what a vector is, which is what you see, NumPy has this, MATLAB, other languages. A vector in that implementation is just a tuple of 3 numbers. So if somebody tells you to add 2 vectors, you just add it element-wise. You just go through the vectors and add them up. But in terms of spatial vectors, that's actually not the right thing to do. Spatial vectors have to be defined relative to a frame. So if you tell me to add 2 vectors, I need to check and see if they're in the same frame. If they're not in the same frame, I can either think of that as an error, so I get runtime checking, and again, helping you debug, or the system can translate a vector from one frame to another by doing a transform. So when you start writing this code, you start to have a feel of what a vector is and what a frame is, especially in an object-oriented language. It's just natural to write down what are the operations that those objects can perform. And then if someone asks you, what's a frame or what's a transform, that's kind of a hard question to answer. But if I can point you to the code, a frame is a thing that performs the following operations. That's one way of defining what it is. And it's one way of understanding the stuff by coding it up.
What do you think is one of the best languages right now to sort of help you start to think in this way?
Well, so Python is my go-to language for a lot of things. And I think it helps with a lot of this, partly because it's readable. And again, I've talked about getting the idea out of your head and into code, but then you have to read it back. And it's also concise. And this is part of the reason I think we can get away from funneling everything through mathematical notation. I think that was necessary at a time with the first generation of languages, like Fortran and C and other languages. They're precise and they're executable, so they have all the benefits of programming languages, but they're not concise. If you take a small amount of mathematics and translate it into C, for example, it gets a lot bigger. Mm-hmm. And you lose something from doing that. I actually brought a quote. I think Paul Graham had a nice quote about this. He said, the more succinct the language, the shorter the program, and the easier it is to load and keep in your head. And I thought the load and keep idea I thought was interesting, because that's the idea that while you're working with the program, you have to keep the whole thing in your head at once. The smaller the program is, the more you can do that. And I think that's where Python and a number of other modern languages make that really possible. So you can really think in Python as if it's your first language.
Right. And so where do you think from Python, where do you think it's going to move forward? Is it going to get more simple, more readable?
Right. Well, no, I'm going to quote Paul Graham again, because one of the things that he said is that the process of programming is not so much that you're taking a solution and just translating it. So what he said is you don't just program down toward the language, you also build the language up toward your program. So I might say, rather than think of it as, what's the next language or what's the next language feature that makes this better, I would say every time you're writing a program, you're building up the solution by every time you add a function to the language, every time you add a class definition, you're effectively making that language more expressive. It becomes a better language for explaining the solution to the problem that you're working on.
Interesting. So there's a lot of talk about what makes the best program, the best code. People think it should be elegant and pretty, or maybe managing complexity. What do you think is the best code? And I know you've sort of talked about this a little bit, but if you could kind of give us like the end answer there.
Yeah, I mean, you mentioned managing complexity. That's something that I think about quite a lot, especially for new programmers. When you talk about coding style, I think people think of it as an aesthetic thing. You want the program to be beautiful, and it's kind of nice. I mean, I think we all appreciate that. But I think the important part is what programming tools give you is the ability to manage complexity. The limiting factor for a lot of programming projects, the limiting factor is our brains, our limited ability to manage complexity. A lot of projects, as they mature, the project gets more and more complex to the point where no one's willing to change the project anymore because nobody has a comprehensive view of the project. It becomes increasingly fragile. And in some sense, that's the end of the life cycle of a project. It eventually collapses under the weight of its own complexity. So what good programming languages do and what good programming style does is helps us to postpone complexity collapse, helps us postpone the point where we can't make any more progress on the project.
Interesting. Okay, surprise final question. Sorry to do this to you, but what do you do when you have to deal with something where there's a lot of legacy code? What would you say to the person that comes into a new job and they're like, hey, fix this up and make it more current?
Right. And that's, I think, the position that most software engineers find themselves in. I teach a lot of beginning programmers, and I have the luxury that I can sit them down in front of a blank screen and they can start from scratch. And so they really can have the whole program loaded in their heads. But then they get their first job, and that's the challenge, is to work with a new system. And I think part of it, probably the first step, is to try to get as much of the system in your head as you can. The other is to find the hooks, that very often when you're working with a new system, you don't need to change all of it. I mean, if you do need to change all of it, something has gone horribly wrong.
Right.
What should be possible is to isolate just the modules that you want to change, the particular feature that you want to add. You need to find the access points, find the hooks, find what's the minimum set of places I need to attach my code. And then you can think of the new code as almost being a separate system. So, I mean, those are my suggestions. But it's a hard thing to teach as well. Again, when we're working with beginners, they're usually working with small pieces of code.
Right.
They don't get the experience of big software projects for a while.
All right, well, great. Thank you so much for coming in. That was fascinating, as usual, to talk to you. And hopefully we'll do it again sometime.
Thanks very much. It was a pleasure.
Thank you.